In our last reading, we looked at this system. We have a U-shaped metal track bathed in a magnetic field. We have a metal bar that can ride the track. When we pull the rod forward, we create a counterclockwise current in the bar. When we push the rod backwards, we create a clockwise current in the bar. This is a simple generator. If we add a light bulb to the rails, we can light the bulb by moving the bar. Suppose we want the light to be on for a long time. We could do that by making the bar really long, but that is inefficient. What's better is to simply shake the bar back and forth. By pulling the bar back and forth, we are making an alternating current in the system. Let's talk about the differences between DC and AC systems. When I connect a capacitor to a light, initially there is a high side and a low side, and the electrons all roll downhill. As the electrons leave the high side, they go to the low side. This makes the high side lower and the low side higher. This keeps happening until the two sides are on the same bleacher, then the current stops. The same thing happens with a cell or a battery, it just takes longer for the bleachers to level out. All three of these examples are DC systems. The electrons go from high to low until it is all over. In AC systems, the electrons still go from high to low, but the trick is that we keep changing which side is high and which side is low. Going back to our bar and rails, we can see that if I pull the bar this way, the top of the bar is high and the electrons would go counterclockwise. If I pull the bar this way, the bottom of the bar is high and the electrons go clockwise. Suppose I pull the bar forward for 5 seconds, and then pull the bar backwards for 5 seconds. That would make a counterclockwise current for 5 seconds, followed by a clockwise current for 5 seconds. The faster I cycle through direction changes, the more often the current turns around. It might be easier to see this with a FET simulation. Here is the FET electromagnet. It is just a coil of wire hooked up to a battery. I can use this slide to move the high bleacher from one side to the other. As I do that, the current changes direction. There's a limit to how fast I can do this on my own. Instead of using the battery and manually moving the bleachers, I can just use an AC source. This device can change the orientation of the electrical bleachers as often as I like. How do you make an AC source? With a coil of wire and a magnet, of course. Here's the FET generator. We see a coil of wire with a meter on it. We also have a compass and a magnet. This time the magnet is attached to a wheel and the wheel is positioned under this faucet. Initially the magnet is not moving and so there is no current in the coil. If I turn the faucet on, the dripping water spins the wheel. As the south pole of the magnet approaches the coil, it induces a clockwise current. As the north side of the magnet approaches the coil, it induces a counterclockwise current. On the wheel, you can see a readout of how fast the wheel is spinning. It is measured in revolutions per minute. At low values of RPM, you can see that the bulb is not very bright and it blinks noticeably. As I use more falling water, which adds more energy to the system, the light gets brighter and blinks faster. I can add more loops of wire to the coil to get it even brighter, but the blinking won't go away. The simulation maxes out at 100 revolutions per minute. Let's talk about an important difference between DC and AC sources. If we light a bulb with a DC source like a battery, the light stays on as the electrons march through it. The FET simulation is suggesting that lights that run off of AC systems blink. The lights in our school and our homes run off of AC systems. Why don't we notice them blinking? With a cell or any other DC source, one side is permanently high and the other side is permanently low. The current always goes from high to low. This is an outlet. At any given moment, one side is high and the other side is low. But from moment to moment, which side is which gets changed. This is a plug from a lamp. The bulb attached to this cord will blink at the rate that the bleachers switch sides. In the FET simulation, the maximum rate was 100 switches per minute. In the outlets in our houses, the bleachers switch sides 60 times each second. That's 36 times faster than the simulation. At that high rate, our eyes can't notice the blinking. But that doesn't mean it's not happening. If I take a high-speed video of the ceiling lights and play it back slowly, I can see that the lights do blink. Here's another interesting thing to think about. In DC systems, we talk about electrons falling from the high side to the low side. Even in situations where you have a high current, individual electrons move very slowly. We describe them as drifting through the system. But eventually, an electron that leaves the high bleacher will go back to the low bleacher. In AC systems, the electrons are constantly turning around. Here's a question. If the wall outlets make them turn around 60 times every second, how far are they actually going to get? Not very far at all. When you plug something into a wall outlet, it is not useful to think of electrons as coming out from one hole and going back in the other hole. When your parents pay their electricity bill, they're not paying for electrons. They're paying for the bleachers to switch sides and shake the electrons that are already in your appliances. We have looked at some small-scale generators. Let's look at some big ones. The FET simulation is an example of a hydroelectric power plant. The hydroelectric plant in Niagara Falls uses water that falls 180 feet to turn 13 generator wheels that produce 2.6 billion joules of energy every second. Wind turbines are becoming more common. There is no substantial difference between a wind turbine and the water wheel. Instead of using water to spin the magnet, you use wind. A single wind turbine can produce 2.5 million joules every second. In many places in our country, people burn coal or wood to produce electricity. The way this works is that you have a closed set of pipes with water in it. Burning the coal turns the water into steam. The steam is pushed through the pipes at high pressure, which spins the magnets, just like the wind turbines or water wheel. A coal plant can produce about 600 million joules every second. In our country, we have 115 operational nuclear energy plants. Radioactive metals give off streams of elementary particles with lots of kinetic energy. This kinetic energy is used to heat a sealed reservoir of water and make steam. The steam spins the magnets. Nuclear plants work just like coal plants in that way. Each one can produce about 1 billion joules of energy every second. To put these big numbers in perspective, in 2019, the United States used 150 million joules of electricity. That means that as a country, we have to produce 4.8 million joules every single second. Before we finish up, let's take one more look at the rail and bar system from the beginning of the video. We described this as a generator. We also recently talked about how you can run a generator backwards as a motor. That's even true for this simple design here. Here I have a lantern battery, 2 wires, some aluminum foil, some tape, and a straw. I cut the aluminum foil into 2 strips to make rails. I taped the rails down so that they are smooth and stationary. I attached the battery to the rails to make one side the high bleacher and the other side the low bleacher. I wrapped the straw in foil to be our bar. When I lay the bar down on the rails, there is a current passing through the rails and the bar. They will get hot, but the bar will just sit there. I'm missing something. I need a strong magnetic field. If I bring this pile of disc magnets over the bar rolls. If I flip the magnets over, changing the dots into X's, then the handle flips and the bar rolls the other way. I'm creating mechanical motion from the magnetic interaction between the electrical current as an object and the agent disc magnets. It's a motor.